Welcome everybody to our next webinar here. We thought it would be a good idea to do one on liquid cooling and direct to chip because there's so much activity in the space and on this topic. And we don't see it slowing down at all. It really has been taken off. So we're going to continue the CDCWT series in September, but we thought this would be a good time just to get out there and get everybody some ideas on best practices, liquid cooling, and talk about some of the things we've seen. And really, my goal is to help you avoid some of the gotchas and problems and things that can arise and help you making some wise decisions in the designs and the plans for these types of systems. So if you have any questions, I'm going to ask you to put them into the chat or the Q&A, and I promise I will get back to them at the end of the webinar here today. If you would like to get a copy of the PDH, CEU, or CPD certificate, I'll give you instructions on how to email to request that, and we will make available copies of the slides and a recording link as well. So yeah, so we'll give you instructions on how to get that, make those requests at the end here, as well as go over any questions that you might have and address them as much as best as we can. So with that, let me jump into, my name's Michael Beatty. I've worked in field sales and service in industrial water treatment for 16 years. The next 13 years after that, I worked advising data center end users and design engineers on data center power and cooling systems, equipment, and design. I've managed several data center design build projects, both greenfield and brownfield. And I started with Nalco in 2020. I primarily support data center design engineers at design firms and hyperscalers and colos and on data center projects and new construction projects. And I just started a new role in July where I'm leading our global new construction team. So excited to talk about this topic, which is so active right now. So what are these loops? In water treatment, we typically will refer to these as what we call process critical closed loops. In data centers, most people know it as direct to chip cooling. There's also immersion cooling and then the critical closed loops, like secondary loops as well. These have a lot of different looks to them, but the primary key is they are critical. These are critical to operation. If something goes wrong, these systems could shut down because of overheating. And so in the data center business, that's what makes these super critical. For people that are newer to data centers, you can see some photos here of some typical applications. Here you can see a data center with the cooling fluid that would go into to cool the cold plates. You've got blue for cool, red for hot, basically. And then over here, you can see pictures of the insides of a typical server where you've got your microprocessing chips on these boards, and then you have cold plates that are basically connected to the tops of the chips to remove heat and reject that heat into a fluid. Here you can see more of a close-up of a cold plate. And normally in the design of these systems, there are what we call CDUs, cooling distribution units, which are between the technical loop and the larger facility water loop is most common how we see these designs in working. Had a good question earlier from a guy that on the earlier webinar, and he said, how come you have these cooling distribution units? Why don't you just run like one big cooling loop and run that everywhere? And I think there's a few reasons why we don't do that, right? One is from the uptime and redundancy standpoint. If you've got everything in one loop and one loop crashes, your whole data center crashes. Whereas if I can split up into different cooling units and then I can have multiple loops. And if I lose one loop, I'm not going to lose all of the loops. So there's some benefit into having some redundancy that way. The other part of this, and it's probably a little bit more critical, is the control of temperature and dew point. It's important for these cooling distribution units not to overcool or subcool the fluids to the point where you get below the dew point and you can begin condensing water on the outside of the equipment, right? That would be a very bad thing. And so the control of dew point, of humidity in the space to make sure that you don't have a problem there and you don't get your temperatures too low is essentially very important. And so that's part of the other aspect of that benefit with a cooling distribution unit. Here's a typical design you might see, and here you'll see we have over here what we would call a technology cooling loop, and in that you could have cooling at the chip here in a rack. You could also have it in a rack where you have a CDU in the rack, or you could have an external CDU. We've seen a few different designs of this nature. That always rejects to some other type loop. It could be a chilled water loop or some other loop that to reject the heat to. And then from there, it could be you could reject the heat to like an air-cooled chiller, to a cooling tower, some type of evaporative system. There's a number of ways to reject the heat from that point. So this is very common in what we see in the designs and distribution of the water flow. So why is this important? Why are we talking about the fluids and managing them properly and treating them properly? And here what you can see is there are problems that can happen if you don't properly manage the water, if you're 100% water, as well as the glycol in these loops. You can run into problems. And so at Nalco, we've worked with several hundred of these types of loops. Most of them have been around in supercomputers for some time, and we're certainly seeing the hyperscalers and colos start to go more mainstream with these types of designs now, right? So there's lots of things that can happen here, and it can be corrosion issues, could be scale issues, it could be microbiological or fouling issues. So we'll dive a little deeper into it, but when you look at the prior slide here and this cold plates, there are very tiny small channels in there. And it's not hard to, like here's a magnification of 50x right here, now 150x here. So if you start to get buildup in these crevices where you have extra heat transfer surface in the cold plate, you're going to have problems and you're going to overheat microprocessor chips. So ideally, the goal is to keep these clean and free of corrosion, scale, fouling, and microbiological growth to maintain the best heat transfer efficiency. A few notes about direct-to-chip equipment. First of all, it's a very precise job. What it's there for is to take the heat out of the process from the microprocessors and reject it elsewhere. You can see the equipment here it can have very large price tags. You could see like in a rack or a few racks, it's easy to get up to in the millions of dollars when you look at what is spent, especially when you look at these NVIDIA Blackwell chips and some of the more advanced chips out there. The price tags are very steep. And so very important to take care of this equipment and ensure its operation. The equipment is designed for high performance and high reliability. So think about it this way. A lot of supercomputers are for research and academic research. And, if you have a problem with a supercomputer and it shuts down because of thermal loads and you need to clean the loop or clean the system, you're gonna inconvenience some people for sure because now their research is delayed. But from a business continuity standpoint, well, they're just going to have a few delays on days. When it comes to business continuity in businesses and critical applications, they can't afford to have these shutdowns. So these systems, when you're looking at it, you need to know what's the nature of how critical this is. Can you handle an unplanned shutdown or not? And most of the folks that I talk to in the hyperscaler co-location world say not. They don't have tolerance for unplanned shutdowns. it's very problematic for SLAs or other aspects of their computing. So there's normally low tolerances for flow and pressure and temperature variations. We're even seeing folks that, they're going to put the CDUs and the pumps and the CDUs and the mechanical equipment, going to start putting that on some type of UPS power. Well, that's a big step, right? Normally, just the IT equipment is on UPS, and you don't put pumps or other cooling equipment on that unless you really want to have like a DRUPS type system for diesel rotary UPS where you can handle mechanical loads. But this is because there's such low tolerances for these direct-to-chip systems. Sometimes you really have to look at, okay, do I need this on uninterruptible power? Because I can't wait 10 seconds or 20 seconds for my generators to kick in and everything to kick back on again. They certainly generate significant heat, and the life cycle normally would be less than 10 years on this equipment. You cannot easily shut down for maintenance, and I mentioned this earlier. Unplanned shutdowns or frequent shutdowns are undesirable typically in these loops. You can have numerous equipment changeouts. If you're replacing servers every 2 years, 3 years, 4 years, which we certainly have seen in the past, well, now you've got a plan for that. Now, if I'm doing 25% propylene glycol and I change all my servers out, what are those new servers going into there have? Are they pre-charged with 25% propylene glycol? Is it properly treated with inhibitors? Do they have water? Do they have nothing? And I just need to add to the system. On a system where you're going to change these chips and servers out regularly, you have to ask yourself that question: what's your long-term plan? And then also dynamic flow patterns. And you can see all kinds of wetted materials in these. I'll talk about that a little bit more on another slide, but there's materials that are desirable and there's materials that are much less desirable. When it comes to the coolant quality and some of the requirements, I share a couple notes here, and I'll share on another slide too about OCP. I'm a big fan of the Open Compute project. I think they've done a lot of good work in the data center community with a lot of experts contributing thoughts and input on standardization and best practices for things like direct-to-chip cooling. So OCP has some guidelines to help, and that was my friend Philip Yu who has been working on that. You want to minimize, the coolant-related problems that you could run into with corrosion and scale and microbial growth. The analytical sampling can be very important in monitoring. And now real-time monitoring is becoming more of a factor here, so that rather than being reactive when I discover I have a problem, how do I be proactive and get some immediate notification when, hey, I'm starting to run into an issue on this closed loop system. I better take a look at it before I have an unplanned shutdown. At Nalco, we are supporters of ASHRAE and OCP. So again, big fans of these and the work efforts happening there. I think it's worthwhile to compare the two most common fluids used for the direct-to-chip applications. We will normally see either 100% water or a 25% propylene glycol blend with water. And they each have their pros and cons. So let's dive into that, because this is really important for you when you're designing. The nice thing about water, it's very efficient from the heat transfer perspective compared to propylene glycol, right? I have a higher heat capacity with water than I do with propylene glycol. So I have a pumping penalty if I use propylene glycol rather than water. So water is desirable in that respect. And with water, it's easy to formulate inhibitors. And it's also easy to dispose of. If you ever have to drain or empty a loop, well, that's pretty easy to do when you have a 100% water-based solution. If you've got a loop, and usually the technical loops don't go outside, but if you've got loops that go outside, well, you've got freeze protection with the glycol, which is nice. You definitely have to use the inhibited glycol. You want the inhibitors in there for corrosion control. I've seen some folks where, I've seen some equipment, CDUs, where people are telling me, oh, there's aluminum in this and aluminum fittings. And I'll tell you, one of the worst things that I heard back from one of my guys in the field was he saw a CDU with a copper aluminum connection with no dielectric in between. Folks, normally on these types of loops, I recommend avoiding aluminum. Aluminum can be a real bear to prevent from corrosion. It's got a tight pH control range, too low. You can corrode, too high, you can corrode. When you use glycol, and if you have aluminum in a system, you have to use a special glycol that is designed for aluminum systems. So aluminum is not as resilient as other metals like copper, or stainless especially. So, really question if I want to use aluminum, do I really need to? What's the good justification for it? Make sure you have dielectric fittings so you don't have any galvanic corrosion cells where you start having aluminum leaking in the future. Aluminum or leaks in electricity don't mix well. One of the major benefit, if not the best benefit of glycol, is it's considered biostatic. And so when you are greater than 25% concentration on the glycol, the benefit there is it prevents the growth of bacteria and microorganisms. Right now, there is not a 100% guaranteed solution for 100% water direct to chip that we could guarantee you will never have bacteria growth. And so when you're evaluating and looking at the risk, the risk that you're willing to take on a design for a system, if you need 100% uptime with only planned shutdowns, then water-based solution is not going to be the best for you. It can be a real challenge in these loops. And the primary reason for that is temperature. These loops can get the temperatures easily 85, 95, 105 degrees. And at these temperatures, the proliferation of growth of bacteria and microorganisms is incredibly fast. We've had some loops where we've treated the loop with a biocide and we've tested it a day later, killed all the bacteria, and within a few days, the bacteria is back up to a super high level. So it's probably the most difficult problem facing the water-based solution where you're 100% water, and the one that I keep leaning on our R&D group to come up with that reliable solution that you can put that in and use water, because then it would be more efficient. So we're actively working on that. Some other thoughts here. So again, with the water base, you're going to have to use biocides, and typically those are non-oxidizing. And they can become, that water can become corrosive in the right conditions. And you can have extreme variability in the water makeup quality as well, which can contribute to scale or other problems in these loops. You definitely have to have frequent or real-time monitoring in a 100% water loop. In a glycol loop, periodic monitoring. But the nice thing is that we actually have real-time monitoring now for glycol loops, because you can have problems with glycol. And if you look at our friends from Dow who worked on the white paper for glycol for OCP, they talk about monitoring certain things and tracking certain things in glycol. And I think that's important. We'll dig into that a little bit more as we go along. From a disposal, you can't just take a used glycol solution and dump it down the drain. You will violate some type of discharge permit. And so you will have to come up with a safe way that you can take whatever fluids that are removed and dispose of them. So another important fact to understand with glycol, especially when you remember that those servers are going to be changed out. There's going to be glycol to be disposed of in those refresh times for servers. So some folks who are new here, this will be a new one for you. This is what we call the water treatment triangle. And it's important to understand this because there are several facets that it can cause lots of problems in cooling water systems. So there are three legs to this: corrosion, scale, and failing. And when we look to treat a system, we look to prevent these three. And the reason you see microbiological is microbiological can have an impact with all three of these in some way. So the microbiological is in the center because it can accelerate or exacerbate any one of the three on here. So in a good water treatment program, we need to prevent all four of these to make sure that we're keeping the cleanest heat transfer surfaces and we're not having corrosion issues with corrosion and on these fins and things like that, for example. Just a couple notes. I mentioned Open Compute Project earlier. There's some white papers that are works in progress. My friend Philip Yu has one going on for water-based fluids. The folks at Dow have one going on for propylene glycol-based fluids. Yeah, I think these will be good sources in the future. Obviously everybody's scrambling trying to get into the best designs and practices, and so these are active work efforts. Also, one of the other fluids that I've seen is the two-phase for liquid cooling and racks. Excelsius is one of the manufacturers I've seen with that design. Haven't seen that take off yet, but I know that they're doing work with NVIDIA and some folks. So I don't think that that white paper has been started yet, but maybe somebody will pick that up. To get to these work streams, you go to Open Compute Project and you look up the work streams, active work streams, and you go to the cooling ones, and then it'll take you to you'll see a link for a wiki page, and you go to the wiki page and you can access everything there. So want to again encourage everybody to get connected with OCP and help contribute in the community. It'll be helpful and beneficial for everybody. So I want to address some of the different fluid quality questions and concerns that come up when we looking at it from a treatment perspective. What are important factors to consider? Well, the first one is pre-cleaning. With all these systems, we always recommend doing a pre-cleaning to remove any mill scale or oils or greases or anything in the manufacturing process with the piping and equipment and things. When you pre-clean, and then you flush, and then you drain, and let's say you're going to do glycol, you're going to add glycol after that. A lot of times it's difficult to drain 100% of the fluid. And so sometimes if you're adding 25% glycol and you add it to a large glycol loop and you haven't been able to get that fully drained, you could end up having a glycol concentration at 23% or 22%. That's a problem. You have to maintain the minimum 25% propylene glycol concentration to maintain the resistance to bacterial growth. If you go below that, glycol can actually, at low enough concentrations, glycol can actually become a food for bacteria. So you really want to avoid that and make sure that you're maintaining the minimum concentration. Very important. Scale. So I've heard this. I've seen a number of specs and things, people wanting deionized water in a 100% water loop. And you can, when you deionize the water, you're removing a lot of impurities, which is great to prevent scale. But there can become an issue where you can accelerate copper corrosion. Copper, as you deionize water and remove all the impurities, it actually gets more aggressive toward copper. That's why you don't see demin and deionized systems piping made out of copper, because it's aggressive and it'll corrode it. So you want to be aware of that copper corrosion mechanism. And if you put inhibitors in there to protect the copper, that will be very helpful and help alleviate that problem. I want to distinguish the deionized water with 100% water as compared to deionized water that's used in diluting glycol. Usually when you're diluting glycol and getting to your concentration, you want deionized water for that, and most of the manufacturers will recommend that. So in that case, as you're diluting glycol, deionized water is definitely helpful for that. Some other corrosion items, stainless steel can actually be corroded if you have too high of a chloride level. So something to be aware of there, and that corrosion gets exacerbated as you go up in temperature. So you need to be aware of that. Plastics and elastomers. So we found with some supercomputers applications where we did some testing and we found increases of suspended solids that had to come from some of the plastics and elastomers. And I'll talk though about those a little bit in the fouling piece. Fouling is basically solids, suspended solids, corrosion byproducts, particles that get in there that can clog up the channels in the cold plates. So to prevent that, we normally like to do some type of filtration. And I'll tell you right now, because this is so young, we're finding people all over the place regarding, well, what filtration level should I filter my technology loop, my direct-to-chip loop at? And let me go over some of the things as I've researched and what I've seen. Most of the CDU manufacturers will have some type of strainer or screen that will filter down in the range of 25 to 75 microns. Okay, so I see that on those folks. When you look at the OCP white paper that Philip's writing, he recommends starting at 5 microns and going down to 1 micron, which I think is a good idea, because even small materials or solids, if they deposit out in those channels, it's going to be very hard to get them out, and that can be a real challenge. To share some of our experience, we've worked with a lot of supercomputers, and I've been seeing a trend in the supercompute world where, because of fouling and some things, that I'm seeing a trend going to 0.5 micron filtration. So it's a very low size. But is it impossible? No, it's actually easy to achieve once you get the system started up and you begin reducing the micron size. Over a period of time, you can easily get down to 0.5 micron. I've had people quite, do I do this? Do I not? I am just sharing with you. These are some of my observations, what I'm seeing and best practices. I think it does make sense to side stream filter these loops and help prevent the potential for fouling in these cold plates. I like the idea of going starting at 5 microns and going down to 1 micron or even down to 0.5. So it's going to help the system to stay cleaner and help your surface, your heat transfer surfaces to stay cleaner. And honestly, when you look at side stream filtration for these loops from a relative cost compared to the tens of millions of dollars of equipment, this is a very tiny cost. So I think it's really worthwhile to consider, and definitely a best practice. Microbiological. So I mentioned earlier, this is the most difficult thing to control 100% reliably in water. If you're designing a system to be 100% reliable, then you're not going to use 100% water. There's too many risks. We see loops that function fine with 100% water, but we also see loops where there can be different problems and there needs to be treatment and flushing and different things. So if you want something that's more reliable, then the PG25 here from the microbiological standpoint is going to be more reliable and prevent bacteria growth. Whenever we develop a solution that we would say is 100% reliable with 100% water, we will be telling everybody. So, because we haven't seen anything out there yet that can make that claim. From a glycol standpoint, monitoring and maintaining concentration. You have to make sure that you're checking, do I have the right concentration of glycol in my loop? There's ways to test it and analyze it. And there's also ways to do real-time monitoring on that. And I'm going to talk about that a little bit later in another slide. And you want to maintain the cleanliness as well in the glycol loop. You're going to want to do side stream filtration again, because you can get buildup. We've seen it where we've looked at particle size analyses over time and saw more and more particles being generated from the materials in the wet ends of the loop. I'm going to take a brief moment here and talk about secondary loops. This one, I focus more on the technical loops and the direct-to-chip loops. But in the designs that I've seen, they always tend to have secondary loops. These secondary loops tend to be large volume loops. They could be anywhere from 10,000 gallons to, 1 million gallons, honestly. So we've seen a number of these for data centers. From the secondary loops, you want to maintain for corrosion control, and there are inhibitors that are very effective at doing that. And also remember, if your technical loops are warm, these loops are also likely to be warm, easily 80, 90, 100 degrees Fahrenheit. And so at those temperatures, you're going to need microbiological control. Two of the primary ways that people I can see doing this, non-oxidizing biocides or chlorine dioxide. And let me give you some brief knowledge on this. So there's different types of biocides. Chlorine dioxide is a dissolved gas, and it has some wonderful properties for being used in closed loops. There's biofilm in there. It can penetrate the biofilm. So most of these large secondary loops have thermal storage with large water storage tanks, which is the perfect environment for materials to deposit on the floor of those tanks. And if you get enough deposit, you can start to form biofilm in there. Chlorine dioxide is great at penetrating that. Non-oxidizing biocides, not as good. The other part is how much you're feeding. So in a large secondary loop, I'll give you an example. I was looking at a project like this not long ago. Normally, when we feed chlorine dioxide, we'll feed it at about a 0.1 parts per million residual. So it's a very low concentration residual that we look to maintain over time. When you slug feed a non-oxidizing biocide, you have to add a certain amount of ppm to have it be effective. And typically that's anywhere from 150 to 500 parts per million. So a much higher concentration that you're going to feed to the non-oxidizing biocide. It could easily be several hundred pounds in a large loop. One of the challenges there is non-oxidizing biocides break down over time. And when they break down, some of their breakdown products can actually become food for bacteria and some microorganisms. So that's a risk that you run with non-oxidizing biocides versus the chlorine dioxide. So there's a reason. I wanted to mention this too. Quick side note. So chlorine dioxide, as we've seen them in large data center loops, is working great. It keeps it disinfected. The reason we don't use it in the technical loops is a few reasons. Right, it's in the white space. So you have precursors to make chlorine dioxide that nobody is going to want to have in a white space in a data center. Normally, that's going to be in a specified location in a mechanical room or like in an outdoor container, then being fed into a loop. So it's very challenging to do like a chlorine dioxide feed into a white space to a technical loop. I think it would work well, but how do you get that in there? That's the challenge. And maintain the residual in such a small loop. That's the other challenge there. In a secondary loop, it works wonderfully. So just understand that in your secondary loops, you're going to have to plan for corrosion control, and you're going to have to plan for microbiological control. I didn't put it on here, but you're also going to want to have some side stream filtration as well. You definitely won't need to go down to 0.5 microns. But going down to at least 5 microns and even down to 1 micron if you have low flows at times can make a lot of sense for these secondary loops. And the last item I have here is real-time monitoring of fluid quality. So we've been actively working on some solutions for how do we monitor both glycols and 100% water in these loops and give the right valuable data. And I'll talk about that on another slide, but this is something where we've seen a real need because these loops are so critical. How do we do that and maintain that? Let's talk a little bit about thermal conductivity. There's a reason we use copper. Why? Because it has a fantastic thermal conductivity. It's fantastic at transferring heat from one fluid to another fluid. You know, aluminum, not super far behind, but again, just not as good as copper, not as effective as copper. Now, take a look and you see these metals and the high levels of thermal conductivity, and then compare them over here to what the thermal conductivity is of scale. So iron oxides, calcium carbonate, calcium phosphate, these are all types of scale. You can see they have lousy thermal conductivities. You get a little bit of scale or fouling buildup in there, and you're going to hinder that heat transfer really quickly. And then the last point here I want to make, look at the biofilm one. Biofilm is 5 times more insulating than mineral scale. So it takes a little bit of biofilm to cause major issues with heat transfer efficiency. Biofilm, it's a major issue. And if you can't handle any risk tolerance for biofilm, then you're not going to use 100% water in your solution. And when we come up with something we feel comfortable, we can guarantee performance on that, we will let you know. Okay, so the prototype monitoring solution here for direct-to-chip cooling. We've been working on a package that really could be plug and play in a rack or in a CDU and in a data center application. So we are working with several OEMs right now in helping them to develop a good monitoring solution for glycol systems, and then also for 100% water systems. So if this is something that is of interest to you, we're not looking to work with folks that just want to do one or two. Sorry. Honestly, we've been partnering with some folks. We're looking for partners because we see a lot of demand for this, and we have limited resources and a lot of workflows on it. So if you're interested in this, let us know. A typical design would monitor pH, conductivity. For glycol, we're going to monitor glycol concentration. We also have a couple other sensors that we're looking at. Really, it depends on who the OEM or who the owner, what they want to monitor. But you can put a what we call an instantaneous corrosion monitoring device for copper. So copper being your most critical piece here, normally as a metallurgy in these loops, you know, monitoring copper corrosion rate is great. Also, in Nalco's heavy industry group, we just developed a unique sensor and rolled it out this year, which will monitor and detect deposit formation. And it'll actually detect inorganic and organic and be able to differentiate between the two, whether it's a scale or whether it's like a microbiological type of buildup. So, you know, we're seeing how, okay, will that fit into this and who is interested in that? Now is the time to talk about it because, like I said, we're seeing so many workflows take off, and a lot of people like, hey, we need to monitor this equipment. How are we going to do this? And make sure that our fluids are good quality. Make sure that after startups and when we do change outs, do we have the right concentration of glycol? So a lot of things and pieces and parts in here to monitor overall. I know on the glycol side, the Dow guys, they have some good pieces there on corrosion coupon monitoring and some things they're talking about. And, you know, that's important. You know, how do you know if you're doing a good job if you're not tracking what corrosion rates look like? And in these loops, copper corrosion is going to be critical to monitor and make sure that that's not getting to a too high of a level. Here's another version of a monitoring loop if somebody wanted something that was outside and could be, you know, have an HMI interface. One of the things that we also do at Nalco is we do digital monitoring. Some places we find that they're uncomfortable with having data go outside the data center. We fully respect that. Other places are like, hey, can you help us monitor our data and track it and then let us know when we have a problem? And so we have several customers set up like that where we have a controller on a system, and if there's a problem, it'll notify our alert monitoring system, and our local representative will get a notice and can stop out the next day to find out what's the problem, what's the issue, what's going on in that particular loop, but also can see the things remotely and see the information remotely with what the alarms are. So we find some folks, they're so busy that they want extra support and help in monitoring these loops. So this is a good fit for them. So when we're looking at the designs for this equipment, when we're coming up with, okay, what's going to fit best in this space, we're really looking at how do we maintain uptime? How do we use water wisely? How are we being the most energy efficient? We actually in Ecolab have our own greenhouse gas monitoring practices that we do, and walking through that. And then asset improvement, and then certainly human health and safety, very important for everybody. So how do we support these high performance compute systems, right, with these high heat densities? Well, normally we have some type of mechanical, chemical treatment program or programs, depending on what's needed for the fluid and for the particular makeup water. And then from a maintenance standpoint, we will track and do analyses, and those analyses can be in our laboratories, and we also can do real-time monitoring solutions on these loops. From a technical expertise, you've got a lot of people here with many years of experience with closed loop systems and these types of warm water systems. And then we have a digital monitoring piece I just mentioned, that how do we track this and help you to monitor your loops, and you can have a large data center where you've got 5 large facility water loops and 100 technical loops. That's a lot of loops to monitor, and to go down and test every one and sample every one. Most places that I see, they don't want a lot of people going into the white spaces and grabbing liquid samples and things like that in white spaces. I don't find people being really big fans of that, if you will. And they want to limit that. And so to be able to real-time monitoring, I think, is a big plus to folks in that want to have more secure spaces that way. As far as our data center team, we support all of these countries around the globe actively in data center projects. So happy to support you on one of those, depending on where you are on the globe and what kind of projects that you have. And then this is just a quick map of our analytical laboratories. So like I said, testing and monitoring, these are important things. And you want to know that you're going to be able to get samples turned over in a reasonable amount of time and getting the analyses. It just kind of gives you a map of where all of our analytical facilities are around the globe. When we're doing the high performance critical closed loop testing, we have certain standards for that we're checking and checking for inhibitors, checking for microbiological growth. So these are things that we turn around pretty often and frequently. We also do testing for glycol and glycol solutions. So something that's important part of what we can do for supporting customers there. And then there's the digital piece, right? What can you monitor and track and help a customer to manage all these loops over a large enterprise. And by doing that monitoring, it really helps to make things easier for operations management folks. Okay, this is my last slide, and just giving you some context here, depending on where you are in the globe and who you might want to talk to. I lead our global new construction team, so you can feel free to email me or reach out to me on any projects for data centers and direct-to-chip. Our lead on direct-to-chip globally is Paul Overbeck, who also has focus in North America and Latin America. In Europe, Middle East, and Africa, it's David McCoon in Scotland. In Greater China and Taiwan, it's Phil Chang. And in Singapore and Southeast Asia, Melwin Long, and Oscar in Australia, New Zealand. So we have a lot of folks around the globe, all positioned to help support you in data centers and these loops. Feel free to reach out either to myself or to one of these folks in your particular region, and we'll be happy to help you out. Monique French, if for those who would like a PDH CEU or CPD certificate, she's the person you're going to want to reach out to. Her email address is mlfrench@ecolab.com. That's mlfrench@ecolab.com. Give her a couple weeks to put those things together, and but she'll be happy to send them to you and for your attendance today. Okay, with that, I'm going to go ahead and jump into the chat and the Q&A. Looks like we have some Q&A here, and we'll go here. Abdallah, is there a simple way to monitor the concentration quality of PG25? Yeah, there's a couple ways, Abdallah. One is you can measure the density of the fluid. You can use a hydrometer and then measure the density, and then you can compare that to a standards chart. That's one of the old-fashioned ways of doing it. Nowadays, refractometers can be used, where you can pass light through there and you can easily tell, hey, what's the concentration of that fluid? So we use an online refractometer in our real-time monitoring solution for propylene glycol 25 to be able to track that. So that's those are the simplest ways for that. I hope I don't say your name wrong. Agus has 25% is recommended minimum glycol, but what is recommended maximum glycol concentration? It's a good question. Normally, the maximum is determined by freeze point, is what I've seen in past experience. I've seen some designs where they have glycol loops going outside to air-cooled chillers and the like. And so depending on the localized climate, that normally determines where somebody's going to have the maximum glycol concentration. And it's real easy you can Google and find tables and charts that show glycol concentration levels and freeze points. So that information is easy to find on Google. And but usually when I see a maximum, that tends to be for freeze point calculation, not for microbial growth. So I hope that's helpful there for you, Agus. Okay, let's jump into the chat. We got a couple things here. Lucas is asking a question. Does Nalco have a recommendation on periodic testing frequency for propylene glycol-based TCS systems, assuming well-designed system material compatibility? Yeah, Lucas, good question. I would say as a standard, twice a year is a good standard to check at a minimum. You could do it quarterly, if you wanted to be a little bit more thorough and frequent, but twice a year would be good. Doing it real time, obviously, that's now you've got it 24/7. So that's my first answer for you. Does this recommendation change if real-time monitoring is deployed? Sure, right? I mean that absolutely makes sense. So if you're going to do real-time monitoring, then the testing of that glycol fluids, I would say then I would probably do it once a year, and that would be because you're going to have that information right in front of you for the concentration. Number 3, are there any forms of side stream filtration you would recommend? I think that depends on the design and the loop. Typically I'm going to look at a cartridge filtration type design. Bag filtration, you can get down to a certain level, but I don't believe you can get bag filtration down to 0.5 microns. I wouldn't want to have anything that's backwashable right on these loops. I don't think there's a need for that. So I would go for like a fine cartridge filtration design on a side stream filter where you take a percentage of that flow and you're running it through the side stream filter. So I've got pushback from different people. That's okay. I can handle it. But regarding the filtration, like I said, when you guys saw those cooling channels for the cold plates, my recommendation is it's worth your while to spend a little bit of money, do some side stream filtration, and help remove any particles or things that are getting in there and keep them from depositing out in cold plates. So that's our professional opinion there.